Hey everybody, thanks for tuning in to Test Tube Plus today. I am Trace, and I'm here with my friend Dr. Ian O'Neill, astrophysicist. Hi, Dr. Ian O'Neill.
Trace, thanks for having me on the show again.
How are you?
Good. Yeah. Very good, actually.
Great. Yeah. Today we're going to talk about a pretty big topic, I think.
Super massive topic.
It's black holes. We're going to talk about black holes. If you'd like to listen to this episode, check the first link in the description. You can also find it in its full entirety, like a whole hour, over on iTunes. It's going to be awesome. But first, I think we should explain what the heck a black hole even is.
Cool.
So, my first intro to black holes was on this great show called Stargate SG-1. Watch it, it's awesome. On Stargate, they dialed into a planet that was orbiting a black hole that for some reason the planet had strayed too close to.
Right.
And what happened was time dilation made it so that they were moving slower on the other side of the Stargate than the people on Earth, and they were watching them like run slowly. Throughout the whole episode, they played out all of these different relativistic physics and how it would be if you could somehow watch people being slowly, falling into a black hole.
Makes sense. Yeah,
it was really, really cool. But even knowing all that, that was for a TV audience today. But there was a time when we didn't even know what a black hole was. In the 18th century, John Mitchell and Pierre-Simon Laplace, they theorized that the universe could hold gravitational fields that were too strong for light to escape.
And they're smart. I mean, they did it before general relativity, quantum dynamics, even modern astronomy. They had no clue.
Yeah,
I find that amazing.
None of that was even part of this. They were just like, you know what, this could be a thing.
Yeah.
It could be a thing. Sitting around at the pub, just
They were
having a
definitely
time.
at the pub, right?
Yeah, probably. So let's break down, in case you're unfamiliar, exactly what a black hole is. Here's how I understand black holes, Ian. Stop me if I'm wrong. Black holes have a singularity.
True.
That is a infinitesimally small point of mass that is so dense and so massive that it's just a huge amount of gravity and everything kind of falls toward it.
Yeah, and it doesn't make any sense physically, really, because it's a point that we can't really probe, and it just basically is the infinite curvature of space-time. It's like a puncture in space-time, I like to think of it. Cool.
And then around the singularity is something called the event horizon, which is really more of an area. Like it's a part of it, but it's not like a physical thing. And the event horizon is the part of a black hole where light is too close to the singularity and can no longer escape. So it appears to be a solid thing.
Yeah. So basically any light that even strays close to this event horizon, it's just an imaginary limit, but that's what actually makes a black hole black, if you think. Because if you can see a black hole, and we're going to mention a little bit about this later on, that we may be able to see a black hole soon, it actually looks like a void in space. And that's because light cannot escape, so we can't see any light inside. So it just looks like a void.
And then after that, is there anything, is that it? Is that the whole black hole?
Well, no, there's some other components. And of course, there's some really crazy physics that goes on at the event horizon, like some crazy magnetism, some exotic physics that we perhaps don't even understand yet because we haven't been able to see it. But just surrounding the event horizon is the Ergosphere, which is basically a region of space-time which is being pulled with the rotation of the black hole. And we believe that black holes do rotate, or at least most of them
Everything
do.
in the universe is spinning, and so it would make sense
we'd
that
assume
black holes would spin too.
So if you imagine, I mean, this Ergosphere is quite easy to imagine. So if you took a spaceship towards the event horizon and you tried to stay stationary, so you're not going to fall into the black hole, but you're trying to stay still, you can't stay still because the space-time is moving. So the actual space-time that you're sitting in is moving, and you're moving around with it. So it's almost like going against a headwind. You have to try and stay still, and you can't do it because space-time itself is rippling around you.
That's crazy.
It's nuts.
There was an analogy used that if you think of space-time as like a piece of rubber, that we're stretching between us, right?
Yeah.
Then the singularity is like this tiny ball bearing that sits on the rubber, but it's so heavy that it pulls it all the way down to the ground. So
exactly.
It's like you can't actually see the ball bearing in this like stretched piece of rubber.
Yeah, so basically, just like a rubber sheet. And any like ball bearing of any mass still has an impact on the curvature of space-time on this rubber sheet. But of course, the singularity is pretty much as dense and massive as it can get, so it just goes straight through to the ground.
Right.
It's basically got infinite curvature.
And so then what you're calling frame dragging is that spinning and affecting what's around it would almost be like, instead of a ball bearing, it's like a pencil that I've stuck through it, right? And I'm turning it, and it's pulling the rubber around.
Yeah, you're kind of creasing it. And it'll be a weird place to hang out.
That's so cool.
Yeah.
Now, are all black holes kind of the same? Are they all the same size?
Nope. Nope, there are several black holes. So, I mean, so go to like a well-known type of black hole, so a stellar mass black hole.
Sure.
And so we're
stellar
talking...
mass, you mean like the size of the sun plus?
Well, about 5 times the mass of the sun. And
Okay.
these are usually generated through massive stars exploding, so through supernovas. Not the size of our sun. Our sun will never turn into a black hole. It's just not massive enough.
Okay, good.
Thank goodness.
I was worried.
No, it's good. And it's not going to die for a few billion years anyway.
Oh,
So
then
it's,
I'm
we're
less
good. We're
worried now.
totally clear. Then you've got the intermediate ones, which are the bridging gap between stellar and supermassive black holes. So the intermediate ones are around about 100 to about 1 million solar masses. So they're still
That's
really
a pretty big range.
So it's kind of surprising that we haven't seen many. So
Yeah.
that's kind of a bit of a mystery in black hole physics.
Then you have the famous supermassive black hole.
My personal
That's
favorite
the
black hole.
center of galaxy black holes, the ones that are just so huge. How big are those?
Well, it's tens to billions of solar masses. These things are huge.
Wow.
And they occupy the cores of most galaxies. And they are intimately related to the evolution of those galaxies as well. So they are of massive importance to scientists. And also our black hole, we have one in the Milky Way galaxy as well. That's called Sagittarius A star, and it is a well-known radio-emitting region in the middle of the galaxy, and it's around about 20,000 light years away. So it's a decent distance away from us,
That's
but we
pretty
can
awesome.
study it from afar.
Yeah, and then there are also micro black holes, which are just little teeny itty bitty black holes
Yep.
that we can actually theoretically have exist in the LHC, the Large Hadron Collider over at CERN.
Yeah, so the theory goes that micro black holes, they're of quantum sizes, and they exist for very, very short periods of time, but that assumes certain physics theories exist. So extra dimensions have to exist for these to exist. And we haven't actually discovered this yet. So this is what the LHC is doing, and they will look for, well, we got some theoretical ideas what to look for,
Yeah.
but as soon as these black holes come into existence, and they just basically disappear very quickly, because they evaporate. They just, using Hawking radiation, they just evaporate very, very quickly. They pop out of existence. They produce some particles that we may be able to detect. And that's
Cool.
one of the signals we're looking for in the LHC.
That's very cool. I like that you said that we may be able to detect them, because
Yeah.
right now we're pretty sure that black holes exist. I mean, we're
Oh.
pretty sure, right?
Yeah, 99% sure.
That's
yeah.
pretty confident.
Yeah, I mean,
but
'cause-
we've never seen one, and which again we'll come back to.
Yeah.
But how do we know that they exist?
Well, there's a lot of indirect evidence. So astronomers have been looking for a long time at potential black holes in the center of galaxies. And one way to look for like supermassive black holes is to look for, look at the stars basically in the center of a galaxy. So you look at other galaxies, you look in the center of our galaxy in the galactic core, and over a period of years, 10 years, as many years as you possibly can, just track these stars as they orbit something in the middle
which
of
we
the
can't
galaxy.
see because
we can't
it
see
is
it.
black.
Yeah, so they are basically orbiting like a ghost. We
Okay.
don't know what it is. There's something very small, but something very massive in the middle that they seem to be pivoting around.
Right.
And we assume that that's a black hole.
Right.
And
so
it seems
we're mapping all of the different gravity in that area, and we're
Yep.
like, okay, this star makes sense. These planets are tugging these stars around, so we've got that.
Yep.
But they're all orbiting this thing that we don't get. That's probably a black hole. We're
Yep.
pretty sure.
Exactly.
There's also other ways to find black holes as well.
And probably the most, the one that's got the most fireworks is to look for active black holes with accretion disks.
Cool.
So if you look at distant galaxies, and if there's a very bright X-ray emitter in the middle of that galaxy, you can pretty much work out that perhaps there's something of great power there. And of course, black holes, they attract a lot of matter, so they form a disk around the black hole as it spins. And this matter is extremely compressed and extremely hot. And this relativistic and hot material produces a wide spectrum of radiation, and one of them is
which
X-rays.
we can then pick up.
And which we detect. Yeah,
Right.
exactly. That's exactly
Oh,
it.
that sounds easy.
Yeah. Well,
With great
no.
power comes great accretion.
Yes.
That's pretty cool.
Exactly.
And the term for that would be, what's a quasar? Is that the term for that kind of
Yeah.
radiation and stuff that we're seeing kind of emanate out from a black hole?
So quasars, were very populous in the early universe because there was a lot of stuff going on back then, a lot of matter falling into black holes, and there were these extremely bright central black hole, central galactic regions that were driven by supermassive black holes with these huge accretion disks. And they basically, you can look, the further you look in the universe, the farther back you look in time, and you can pretty much look in the first couple of billion years of the existence of our universe and find that there were very active black holes back then.
That is super cool.
Yep.
There's also the gravitational lensing. I know all about that. We've talked about that over on D News as well, and that's that gravity actually warps space-time, similar to that rubber sheet analogy we were using earlier, and that warping is visible from far away in that it literally looks like a lens. It magnifies and kind of changes how things look behind it.
Exactly. I mean, like you've probably seen the images from the Hubble Space Telescope, where the Hubble looks in a distant part of the universe, and it sees these arcs of light in its observations, and you're like, wow, what could be causing that? And yeah, as you say, it's basically a gravitational lens. It's basically a point of intense gravity causing this warping of space-time, creating a lens. And if you think you're looking through a lens and you put it in front of a candle or a light, you get these arcs.
Yeah.
And when Hubble saw these, this was a very big moment for Einstein's general relativity, because this is one of another piece of evidence to prove that his theory was correct.
And Einstein's general theory of relativity is what we are going to talk about on this next episode of Test Tube Plus. So make sure you come back tomorrow and subscribe so that you can get that episode in your inbox. We're going to talk about relativity and a bunch of other really complicated and awesome science. So make sure you come follow Ian and I on Twitter. You can find me at Trace Dominguez. You can find Ian at Astro Engine, and come back tomorrow for more science. If you can't wait until then, make sure you watch last week's episodes all about conspiracy theories. It was awesome. A lot less science, but just as awesome. Thanks for watching.